Okay, so composite functions are basically functions of functions. Yeah, so we can look at the Ed Rollo video if you want to have a more detailed explanation. But I guess if we consider the f of x function that's just listed there, we could think of that as a they talk about it here? Yeah, they talk about it here. A combination of the functions x plus 3 and the combination and x squared. And we're just substituting x plus 3 into x squared, which is sort of what this notation says, hg of x. All right. So our composite function notation might use f of g of x. In other words, we substitute the g of x function into f, and we might also call that f of g, and also g of f of x, which means we substitute f of x into g, and we call that g of f. All right. So we can actually evaluate, we can combine any two functions and work out a composite function. Okay, and we show that really clearly here in example 11. So my first function there, f of x, x squared minus 2. And so f of g can be written as f of g of x. So we're clearly substituting g of x into f. So the g of x function, the square root of 2x plus 1, substituted in for x, which is what we've done there. And we get the square root of 2x plus 1 all squared, so the square root and square cancel. So I get 2x plus 1 minus 2, so I get the function 2x minus 1. That's my composite function. And so then if I want to evaluate that at a point, I just substitute 2 in, and I get 2 times 2 minus 1, which if you weren't concentrating, you might write down 5, but we might put down 3. Yeah? All right. Similarly, we can work out g of f. G of f can be written as g of f of x. Yeah, so that sort of gives you the order. Substitute f of x into the function, which is what we've done. We've substituted x squared minus 2, which is the f function, into the g of x function. So multiply that through, I get 2x squared minus 4, which gives me 2x squared minus 3, the square root of that. Okay. Then if I want to work out g of f of 0, I substitute 0 in for x, which will give me 2 times 0 squared minus 3, which is the square root of negative 3. Clearly, the function is not defined there. And that leads us to, I guess, a really significant element of composite functions is that even though we can find rules for everything, it's not to say that the function necessarily exists. Yeah? So let's think about even this last one here. All right, so even though that if I work out at x equal to 0, okay, at x equal to 0 is a part of the domain of f of x, yeah, it isn't a part of the domain of g of x. All right, so what we're thinking, all right, is that given that we've substituted, let's come in here for f of g of x. Given that I've substituted g of x into the function f, so what we're really doing is we substitute a value into g of x. Okay, so there's the domain of g. It generates a range value, and then I substitute that range value into f. Yeah. So that means that these range values that g provide have to be inside the domain of f, which is this statement here. The range of g of x has to be a subset of the domain of f. So the values that g of x produce have to be inside the domain of f, otherwise we have an issue. Right. Similarly, for g of f of x, the range of that function there, the range of the inside function, has to be inside the domain of the outside function. All right. Otherwise, we have existence issues like we did here with g of f. All right. So whether a composite function exists, strongly urge you to do a little domain range table for the two functions involved. All right. And then you check. All right. So knowledge of graphs is crucial. All right, so in both of these instances, the domains we've been given. So x is an element of R, and it's a straight line graph. So the domain is, the range is also an element of R. I've got the square root function, where the domain is greater than or equal to 0, and my range is also greater than or equal to 0. So for f of g to exist, so for f of g of x, we need the range of g to be a subset of the domain of f. The range of g from my table is R, a subset of the domain of f, which is 0 to infinity, which is false. Therefore, it does not exist. All right. We might come down for g of f now. I'm on the wrong spot. So for g of f of x, I need the range of f to be a subset of the domain of g. The range of f, 0 to infinity, a subset of the domain of g, which is R, which is true, therefore exists. Okay, just thing to highlight, if ever you need to prove that a composite function exists, it's not enough just to state that and then that. Yeah, you must have the values in there. It must be clear that you knew what the domain of f is and you knew what the range of g is, or whatever ones we're looking at. All right, so I've got the composite function that is defined, state the domain and the rule. Okay, so the domain of the composite function, so if we think about what domain is the significant, so the domain of g of f is equal to the domain of g, okay? Because that's the one that's generating all the values, and the domain of g is R. And the rule itself for g of f of x is 2 times, put f of x in there, so 2 root x minus 1, which is just equal to 2 root x minus 1. The range of that function is just going to be determined as you would normally determine a range. You'd have to sketch the graph and come up with it. So 2 root x, well, it's almost the thing that we've got above there, but shifted 1 unit down, isn't it? So we might have a range of -1 to infinity, as long as 0 is a part of it. It is. Okay? So that's the process. Let's have a look at 13. All right, state why g of f is not defined. Step 1, create our domain range table. So again, there's a domain R, and here's my domain 0 to infinity, so I can put those in. For x plus 1, if I've got a domain of R, I've got a range of R, and for the natural log of x, something like that, we've got a domain of R. All right. Why is g of f not defined? So we need, for g of f, we need the range of f to be a subset of the domain of g. The range of f is R, has to be a subset of the domain of g, 0 to infinity, which is false. Therefore, it doesn't exist. Define a restriction for f of x such that g of f is defined. Okay, so what's the issue? That range of fr, that one there, we have to restrict to be 0 to infinity. All right, so let's have a look at that graph. That graph is x plus 1, -1, 1. And I need the range of this function to be between 0 to infinity. So the range has to be that section, yeah, which is clearly this part of the graph there. So if I restrict the domain to be those values, yeah, So therefore, if the domain of, we'll call it f star, is equal to -1 to infinity, the range of f star is equal to, now hang on, well, we just have to make an adjustment here, is equal to 0 to infinity, yeah? But we can't have 0, so I've got to make everything a round bracket. So if I make that a round bracket there and a round bracket there, let's make it a round dot there. So there's my new domain of f. So if I have a little function here, f star, the domain of f star is from -1 to infinity. The range of f star is from 0 to infinity. And now that is a subset of g. So the composite function would now exist. G of f itself will be equal to, g of f will be equal to the natural log of 2 times x, which is equal to the natural log of 2x plus 2 will be fine. All right? Okay. And that process is really common, where we have to apply a restriction to an existing function to make the composite exist, or the inverse exist, as we'll get to later. All right, we've got another function here, another composite function. So the first thing we did was fill in our domain range table. So we've got our domain and range of everything there. Right, find the least value of a such that the composite function f of g of x exists. So again, for f of g, I need the range of g to be a subset of the domain of f. The range of g is from a plus 1 to infinity to be a subset of the domain of f, which is from 0 to infinity. So therefore, I need a plus 1 to be greater than or equal to 0, don't I? So a has to be greater than or equal to -1. All right, so if that's the case, so we could do a quick sketch even, really, couldn't we? In fact, it's nearly the function we've got there. So as long as a is greater than -1, I've got the graph of x plus 1. If a is greater than -1, I've got that. And the domain of that, the range of that is from 0 to infinity, which is what I needed for f. All right. Lucky last. Again, similar sort of problem. I've done my domain range table. Hopefully I've done them right. 1 over the square root of x minus 1. Now we might be not really all that familiar with the graph, but clearly I need x minus 1 has to be strictly greater than 0, because I can't get the square root of a negative number, and I can't have 0 in the denominator this time. So I need x minus 1 to be greater than 0, so x has to be greater than 1, which is what I've got. And if we think about, whilst we don't really know what that graph looks like, 1 over root x, we do know that the square root of x is between 0 and infinity, and it won't be 0. So 1 over a really, really small number, which you can get, is going to be really big, and 1 over the square root of a really big number will be really small. So we're just going to have 0 to infinity as my range. Again, if f of g of s has to exist, I need the range of g to be a subset of the domain of f. So the range of g is a minus 1 infinity to be a subset of the domain of f, which is 1 to infinity. So I need a minus 1 to be greater than or equal to 1. So a has to be greater than or equal to 2. All right, so what does it say? It just says to find a. So there we go, similar sort of problem. All right, so it's a massive skill. restricting our domains to have our composite functions exist. So give that a little bit of time and effort. Off we go.